United States, the nominal voltage for three-phase electrical systems is 480 volts. However, motors are typically designed and rated for a voltage that is slightly lower than the nominal voltage to account for voltage drop and other factors. Article 430.7 B1 of the National Electrical Code requires that motors with nameplate ratings equal to or less than 500 volts be connected to a circuit with a voltage not more than 110% of the motor nameplate voltage. In your case, the motors are rated for 460 volts. The plant motor control center is rated for 480 volts. This meets the NEC requirement because 480 volts is within 110% of 460 volts. 460 times 1.1 equals 506 volts. The voltage drop in the supply cable also contributes to the discrepancy. When the motor is running, a voltage at the motor terminals will be slightly lower than the voltage at the motor control center due to voltage drop in the cabling and connections. This voltage drop will further reduce the voltage seen by the motor, bringing it closer to the rated voltage of 460 volts. Motors also have a voltage tolerance that allows them to operate within a certain range of voltages without damage. Typically, motors can withstand a voltage up to 10% above their nameplate voltage without experiencing any issues. Connecting a 460-volt motor to a 480-volt supply is permitted under NEC regulations provided that the voltage drop in the supply cable is taken into consideration. The voltage tolerance of the motor also contributes to the ability to operate safely and efficiently at the higher voltage. To further elaborate, we should consider the various factors in more detail. Firstly, the NEC provides guidelines for ensuring safe and reliable electrical installations. The allowance of a higher supply voltage than the motor's nameplate rating within limits is rooted in practical considerations. Secondly, voltage drop is an inevitable phenomenon in electrical circuits, especially over longer distances. Cables have impedance, and when current flows, a voltage drop occurs. This means the voltage at the motor terminals is less than the source voltage. Thirdly, motor manufacturers design motors to tolerate some voltage variation. A plus or minus 10% tolerance is common. This ensures the motor operates reliably despite voltage fluctuations. Fourthly, the NEC 110% rule allows for some headroom above the motor's nameplate voltage, recognizing that the voltage at the motor terminals under load will likely be lower due to voltage drop. To provide an example, consider a 460-volt motor connected to a 480-volt supply. If the voltage drop in the cable is 20 volts under full load, the motor effectively sees 460 volts, which is within its rated voltage. Also, a 460-volt motor with a 10% tolerance can handle up to 506 volts without damage. This is calculated as 460 volts plus 10% of 460 volts. Voltage drop calculations are critical in electrical design. Firstly, cable size is a key factor. Larger cables have lower resistance and thus less voltage drop. Secondly, cable length also plays a role. Longer cables will have more voltage drop. Thirdly, the load current influences voltage drop. Higher current leads to greater voltage drop. Fourthly, power factor affects voltage drop. Lower power factor increases voltage drop. Several methods exist to calculate voltage drop. Firstly, using voltage drop calculators, which are available online or in electrical design software. Secondly, applying the voltage drop formula, which considers cable resistance, length, current, and power factor. Thirdly, consulting NEC Chapter 9, which provides tables and formulas for voltage drop calculations. To minimize voltage drop, you can firstly use larger conductors, which reduces resistance. Secondly, shorten cable runs, which minimizes the overall resistance. Thirdly, improve the power factor by using power factor correction capacitors. Fourthly, optimize the circuit design to reduce current flow. Motor performance can be affected by both undervoltage and overvoltage. Firstly, undervoltage can cause reduced torque, overheating, and potential motor failure. Secondly, overvoltage can lead to insulation breakdown, reduced motor life, and increased energy consumption. Voltage imbalance in three-phase systems can also impact motor performance. Firstly, it causes increased motor current, leading to overheating. Secondly, it results in reduced torque and efficiency. Thirdly, it can lead to premature motor failure. Several NEC articles are relevant to motor installations. Firstly, Article 430 covers motors, motor circuits, and controllers. Secondly, Article 430.7 discusses motor nameplate information. Thirdly, Article 430.12 covers motor terminal housings. Fourthly, Article 430.22 addresses motor circuit conductor sizing. Ensuring proper grounding and bonding is crucial for motor safety. Firstly, it provides a low impedance path for fault currents. Secondly, it reduces the risk of electric shock. Thirdly, it helps prevent equipment damage. Overcurrent protection is vital for safeguarding motors and circuits. Firstly, fuses and circuit breakers protect against overloads and short circuits. Secondly, they must be sized appropriately based on motor characteristics and conductor ampacity. Thirdly, the NEC provides guidelines for overcurrent protection sizing. Motor control centers provide centralized control and protection for multiple motors. Firstly, they house motor starters, circuit breakers, and other control devices. Secondly, they offer enhanced safety and convenience. Thirdly, proper motor control center design and installation are essential. Harmonic distortion can impact motor performance and efficiency. Firstly, harmonics create additional losses in the motor. Secondly, they can lead to overheating and reduce motor life. Thirdly, harmonic mitigation techniques may be necessary. Energy efficiency is an important consideration in motor selection and operation. Firstly, energy-efficient motors can save significant energy and money over their lifespan. Secondly, proper motor sizing and load matching improve efficiency. Thirdly, variable frequency drives can optimize motor speed and energy consumption. Regular motor maintenance is crucial for reliable operation. Firstly, lubrication reduces friction and wear. Secondly, inspections identify potential problems before they become major failures. Thirdly, proper record keeping helps track maintenance activities and motor performance. Troubleshooting motor problems requires a systematic approach. Firstly, check the power supply voltage and current. Secondly, inspect the motor windings for insulation damage. Thirdly, test the motor control components. Variable frequency drives, also known as VFD, are used to control the speed of AC motors by varying the frequency and voltage supplied to the motor. Firstly, VFD allow for precise speed control, optimizing motor performance for specific applications. Secondly, VFD can significantly reduce energy consumption by matching motor speed to the actual load requirements. Thirdly, VFD can improve motor starting characteristics, reducing stress on the motor and driven equipment. Fourthly, VFD offer advanced control features such as acceleration and deceleration ramps, torque limiting, and process control. Several types of motor starters are used to safely and reliably start motors, limiting the inrush current and protecting the motor and associated equipment. Firstly, across-the-line starters directly connect the motor to the full voltage supply, providing the simplest and most economical starting method for small to medium-sized motors. Secondly, reduced voltage starters, such as auto-transformer starters, resistor starters, and part winding starters, reduce the voltage applied to the motor during startup, limiting the inrush current. Thirdly, solid-state starters use electronic components to gradually increase the voltage applied to the motor, providing smooth and controlled starting. Fourthly, variable frequency drives can also be used as motor starters, offering the most advanced and flexible starting method. Proper motor cooling is essential to prevent overheating and ensure reliable operation. Firstly, air-cooled motors use fans to circulate air over the motor windings and frame, dissipating heat. Secondly, liquid-cooled motors use a liquid coolant, such as water or glycol, to remove heat from the motor, providing more effective cooling for high-power applications. Thirdly, forced air cooling uses an external fan or blower to provide additional airflow over the motor, improving cooling performance. Fourthly, totally enclosed fan-cooled motors are designed to prevent the ingress of dust, moisture, and other contaminants, making them suitable for harsh environments. Motor bearings support the rotor and allow it to rotate smoothly. Firstly, ball bearings are commonly used in small to medium-sized motors, offering good performance and durability. Secondly, rollo bearings are used in larger motors, providing higher load carrying capacity and longer life. Thirdly, sleeve bearings use a layer of lubricant to support the rotor, offering quiet operation and good damping characteristics. Fourthly, proper lubrication is essential to maintain bearing performance and prevent premature failure. Motor insulation protects the motor windings from electrical breakdown and short circuits. Firstly, various types of insulation materials are used, including varnish, epoxy, and thermoplastic coatings. Secondly, the insulation system must be designed to withstand the operating voltage, temperature, and environmental conditions. Thirdly, insulation resistance testing is used to assess the condition of the insulation and detect potential problems. Fourthly, proper maintenance and repair of motor insulation are essential to ensure long-term reliability. Motor vibration can indicate mechanical problems such as misalignment, imbalance, or bearing wear. Firstly, vibration analysis uses sensors and software to measure and analyze motor vibration, identifying the source of the problem. Secondly, vibration balancing corrects imbalance in the rotor, reducing vibration and improving motor performance. Thirdly, shaft alignment ensures that the motor shaft is properly aligned with the driven equipment, minimizing stress and vibration. Fourthly, regular vibration monitoring can detect potential problems early, allowing for timely maintenance and repair. Motor efficiency is the ratio of mechanical power output to electrical power input. Firstly, high-efficiency motors are designed to minimize losses and maximize energy savings. Secondly, motor efficiency is affected by factors such as motor design, load, and operating conditions. Thirdly, motor efficiency standards, such as NEMA Premium, specify minimum efficiency levels for different motor types and sizes. Fourthly, selecting the right motor for the application and operating it at its optimal efficiency point can significantly reduce energy consumption. The NEC provides specific requirements for motor disconnecting means, ensuring that motors can be safely disconnected from the power supply for maintenance and repair. Firstly, the disconnecting means must be readily accessible and capable of being locked in the open position. Secondly, the disconnecting means must be rated for the motor's voltage and current. Thirdly, the disconnecting means must be clearly labeled to identify the motor it controls. Fourthly, multiple motors can be connected to a single disconnecting means under certain conditions. The NEC also addresses motor overload protection, which protects motors from damage due to excessive current draw. Firstly, overload protection devices, such as thermal overloads and electronic overloads, trip when the motor current exceeds a predetermined level. Secondly, overload protection devices must be sized appropriately based on the motor's nameplate current and service factor. Thirdly, overload protection devices must be coordinated with the motor's starting characteristics to prevent nuisance tripping. Fourthly, the NEC provides specific requirements for motor overload protection sizing and installation. Motor grounding ensures that the motor frame and other non-current carrying metal parts are properly connected to ground, providing a safe path for fault current and reducing the risk of electric shock. Firstly, the grounding conductor must be sized according to the NEC. Secondly, the grounding connection must be made to a suitable grounding electrode. Thirdly, the grounding system must be properly bonded to other metal parts in the vicinity. Fourthly, regular inspection and testing of the grounding system are essential to ensure its effectiveness. Motor testing is performed to assess the motor's condition and performance, identifying potential problems and ensuring reliable operation. Firstly, insulation resistance testing measures the resistance of the motor windings to ground, indicating the condition of the insulation. Secondly, winding resistance testing measures the resistance of the motor windings, detecting shorts, opens, and imbalances. Thirdly, surge testing applies high voltage surges to the motor windings, detecting weak spots in the insulation. Fourthly, vibration analysis measures the motor's vibration levels, identifying mechanical problems. Motor nameplate information provides essential details about the motor's characteristics and operating parameters. Firstly, the nameplate includes the motor's voltage, current, horsepower, speed, frequency, and insulation class. Secondly, the nameplate also includes the motor's service factor, which indicates the amount of overload the motor can handle. Thirdly, the nameplate information is used to select the proper motor control and protection devices. Fourthly, it is essential to understand and interpret the motor nameplate information correctly. The NEC provides guidelines for selecting the appropriate motor enclosure for different environments. Firstly, open drip-proof enclosures are suitable for clean, dry indoor environments. Secondly, totally enclosed fan-cooled enclosures are suitable for dusty or damp environments. Thirdly, explosion-proof enclosures are required for hazardous locations where flammable gases or vapors may be present. Fourthly, the enclosure must be properly selected to protect the motor from the environment and ensure safe operation. The power factor of a motor is the ratio of real power to apparent power. Firstly, a low power factor indicates that the motor is drawing more current than necessary to perform the work. Secondly, a low power factor can lead to increased energy costs and reduced system capacity. Thirdly, power factor correction capacitors can be used to improve the power factor. Fourthly, utilities often penalize customers with low power factors. Harmonic distortion is the presence of harmonic frequencies in the electrical system. Firstly, harmonics can be generated by nonlinear loads such as variable frequency drives and electronic equipment. Secondly, harmonics can cause overheating of transformers, motors, and other equipment. Thirdly, harmonics can also interfere with electronic equipment. Fourthly, harmonic filters can be used to reduce harmonic distortion. Motor surge protection protects motors from voltage surges caused by lightning strikes, switching events, and other disturbances. Firstly, surge protection devices divert the surge current away from the motor windings. Secondly, surge protection devices must be properly sized and installed. Thirdly, surge protection is particularly important for motors connected to long overhead lines. Fourthly, regular inspection and testing of surge protection devices are essential to ensure their effectiveness. When selecting a motor, it is important to consider the load requirements, including the horsepower, speed, and torque. Firstly, the motor must be sized appropriately to handle the load. Secondly, the motor's speed must be compatible with the driven equipment. Thirdly, the motor's torque must be sufficient to start and accelerate the load. Fourthly, it is often beneficial to consult with a motor manufacturer or application engineer to select the optimal motor for the application. Proper motor installation is essential to ensure reliable operation. Firstly, the motor must be mounted securely on a stable foundation. Secondly, the motor must be properly aligned with the driven equipment. Thirdly, the motor wiring must be properly connected and protected. Fourthly, the motor must be properly grounded. Regular motor maintenance can extend the motor's life and prevent costly downtime. Firstly, the motor should be lubricated regularly. Secondly, the motor should be inspected for signs of wear or damage. Thirdly, the motor should be kept clean and free of debris. Fourthly, the motor's performance should be monitored and any problems should be addressed promptly.